supposed to like rearrange the equation to a different form?
Yes, basically. Let's see.
I have it right here if you want to look at it.
Yeah, could you? So the Chernoff bond question asks you to show, I'm not going to, of course, I'm not going to solve it, I'll just try to make you think about what compares this to what we did in class. So in class, we saw the Huffing bond being applied to something like the probability that the true probability is greater than P hat plus epsilon is less than something like that. So notice that this is an additive. So this is additive. It's saying, well, what's the probability that the difference, I'll give this to you in a minute, what's the probability that the difference is more than epsilon? Here, instead, the question is asking you for a multiplicative thing. Probability, so instead of P and P prime, error D is greater than error S. This is what we saw in class. What this question is asking you is the probability that error D is, let's see, is greater than error a multiplicative version, and it's asking you to show something about this kind of a statement, and then you have to apply a similar sort of form. But it turns out in the question you're given a Chernoff bond hint, and you have two of them. You have probability. So using the notation in the question, this thing is like P, this thing is like S divided by F. But the question tells you something about probability of S over M greater than 1 plus gamma P, and something about probability of S over M less than 1 minus gamma times P. Notice that between here and here, the terms are interchanged. So you need to do some algebra here. Think about what else you have in play. You know, for example, for this form, you know that 0 less than equal to gamma less than equal to 1. That's given to you. I mean, so everything below the line is part of Chernoff bond. Everything above the line, let's look at this. You have a gamma top on top, you have an epsilon. Sorry. Yeah. Oh no. You have an epsilon on top. You know that the error epsilon in the learning situation is between 0 and 1. In the Chernoff bond works with gamma between 0 and 1. Now clearly, the same gamma, epsilon equals gamma does not work because the signs are different, the direction. The S over M, on one hand, let me just write it again, because on one hand you have S over M this is what so this is Chernoff, and what we want is P not gamma but epsilon. And you need to rearrange these. So clearly gamma equals epsilon doesn't work, but maybe some other value of gamma works that is connected to epsilon. And you need to think about these two aspects and kind of rearrange this so that this inequality starts to look something like that by playing with the gamma. And this is a big hint. It took me a while to figure that out, but think about what I just said. Okay. Other questions? Yes.
The exponent has a 2 and a 3. That's not a typo, right?
No, that's not.
Okay.
Yes. Other questions?
Did that all get recorded?
I bet it did.
Yeah.
I bet it did. So, yeah. This is the advantage of coming to class. You don't need it to be recorded.
Well, I couldn't write things down while
Oh,
you
sure,
were talking.
yeah. Oh, that's right, yeah. Other questions about the homework? Have people started the VC dimension part of it? And any questions about that?
Actually, just about the first one.
What's
Yeah.
the first one? Could you remind me?
It's proven that.
Oh, something about a factory and some robots picking parts and stuff.
No, the first one in the VC dimension.
Oh, okay, yeah.
So that's the bounding.
The double interval?
You want to see it again?
Oh, this is the finite hypothesis class.
Yes,
Yes.
and prove that it's strictly, or
Yes,
at most,
yes.
log.
And the hint is actually a big hint.
Sine of C.
The contradiction, just prove it by contradiction. That tends to work out pretty easily. When I say easy, but it tends to be not hard. Assume, for example, that the opposite of that statement is true, that the VC dimension is more than log size of the hypothesis class. Then, the proof of this just shows up by applying the definition of VC dimension. The VC dimension has two sides. So if this means that a concept whose set of examples of size that much can be shattered. The VC dimension is more than some number, means a set of examples of that size can be shattered. What is the definition of shattering? Then you just go, keep applying the definitions, you'll end up with a contradiction. Other questions? And I know I'm deliberately being kind of obscure here because if I say more, then I'll basically end up announcing the answer.
On the second one in VC dimensions, I don't know if I'm the only one, but it was just hard for me to understand exactly what a hypothesis class is. Considered.
Yeah, let me look at it again. I've forgotten it already.
It's kind of split between here and there.
Okay.
So you might have to scroll up to get the first part of it.
Right. So this is saying, let me just write down the thing and then I'll explain it to you. I'll just write the first one. H. Can I erase this? You know what would be cool if I can save these things, but I'm sure it's possible, I just don't know how. So, equals K of X is all hypotheses. This is just a notation for saying all functions, such that the number of places where the function says 1 is equal to K. So the notation is a bit more confusing than what is optimal, so let's just write this in. And there was a slight fix such that number of functions. Okay, let's parse this because so I think I posted a new version where there was a fix in this. Let's parse this.
Is that a K inside the second curly brace? What letter is that? Just inside the second curly
This one?
brace. Yeah. What is
It's an
it?
X.
Oh, okay.
Yes, this is an X. So this simply says, let's just first parse this one. The set of examples where the function says 1. Right? Then let's go one outside. This part says the number of examples of this kind. So this whole function class is the set of all functions such that the number of examples where it maps to 1 is exactly equal to k. Does that make sense?
Yeah.
Yeah. And remember that the instance space is finite here, right? This is also finite. Which means you can use the previous result, and you need to think about counting the number of functions.
Okay, that helps. The notation was just.
Yes, the notations. Yeah, there was also a bug. I think we've fixed it, right? And I've updated the website. The previous version did not have these curly brackets, and without the curly brackets, it becomes way more complicated to use. All right, I feel like I've spent enough time on the questions. I should also advertise that there are office hours today. I think Samarth, are you here? Yes, he's looking forward to meeting you guys. And I just like putting my tea in the book. The other announcement is about projects. There's an intermediate report that's due. I pushed back the date to November 8th. That will kind of put it right in between when the project proposal was made and when the project final thing is due. So the intermediate report is literally in the middle. What I want to see in the intermediate report is any progress that you've made, and there are unacceptable answers there, which is I have done nothing for the project. You should know, most of you are working on data, doing some experimental stuff, and if you do not have the data set by then, you will definitely not get points for that, for the intermediate report. You need to have your data set. Tell me about your data set. What's your data set like? What's the, what do you call it? How many examples do you have? What's the baseline? So for any sort of a machine learning problem that you apply in the wild, what you need to think about is what are the baselines? The most obvious baseline that you can think about is all predict the majority class. Predict every example has a majority label. Because you cannot do worse than that. You should not be doing worse than that. So the majority label simply says you take the training set and count which label is the most frequent, and pretend that that is the label of all the answers. How badly will you do on the training set in that case? That is simply the fraction of examples that do not have majority label. That's your error, right? So you should give me the performance of the majority baselines in your intermediate report, because in some sense, if you train a classifier, let's say you train a classifier and you spend like 3 days doing cross-validation and training and all that, and at the end, your classifier does worse than the majority baseline. Kind of sad, right? So this is like a minimum level that hopefully your learning algorithm does better than. Very often that ends up being pretty much the only baseline it beats, because sometimes the learning problem is so difficult that it becomes hard for you to do any better than just, any better than slight improvements over the majority baseline. But in any case, for the intermediate report, you should tell me what's the majority baseline. You should also tell me what progress you've done. I mean, for example, have you pre-processed the data? Have you done any sorts of feature extraction, transformations? Have you tried out using some simple learning algorithms? Hopefully, you've done at least some of that. But the point of the intermediate report is to force you into activity, because otherwise, I have seen cases where people start doing the class project the day before it's due, and it doesn't go well. So, to repeat, you should have your data, you should have done some data mangling, give me some statistics. In some sense, think of me as a person who does not have access to your data, and I would like to understand your data. I'm not allowed to see your data, so I should get a feel for what your data is like. You should describe your data in a way that I can understand. That's really what I'm looking for. Okay? Any questions about that? And for the other one, the competitive project, there's already some interesting progress on that. Every day I wake up and one of the part of my routine has now become checking what's the progress on Kaggle. It's right now we are at 82 or something %, and there's bitter fight for first place. It's not, the crown has not been stolen yet, but that's only because like only 11 of you are participating, but I expect more of you to. I know that more than 11 of you have signed up for the competitive project, and the terms of the deal were that by the intermediate report you should have tried out at least 2 algorithms. So you should have done that. All right. Any other questions? Any questions about any of the stuff? Yes.
How long should the report be?
Oh, there must be something on the website. I vaguely remember saying no more than 2 pages. One other thing that the intermediate report should tell me is, this is important actually, is your evaluation plan. How do you plan to evaluate your classifiers? So any test train splits, for example, that you may have already done. So the reason for that is sometimes accuracy might be the right way to evaluate your classifier, sometimes it's not. Sometimes your task might come with an evaluation that is natural. So if you're doing regression, for example, mean square error seems like a natural way of evaluating your classifier. So you should have a subsection on how you plan to evaluate your classifiers, and that should be how you'll evaluate your majority baseline. If you're doing regression, for example, majority is a meaningless baseline. The better way of doing that is the mean. Just take the mean of all the labels of the training set, and that's your brain-dead baseline. So come up with brain-dead baselines, come up with an evaluation plan, describe your data set, and make it no more than 2 pages. Okay? And I say no more than 2 pages, but that does not mean 1 line is good, because you have to give me all this information. Alright, so that's a lot of announcements. I had not expected it to go for this long. Today we're going to start, we're done with computational learning theory, and we're going to start a new section. This is on boosting, and more broadly on the idea of ensembles. So the plan, and my hope is to finish this entire lecture today. Yes?
Did we cover basic dimensions in the last class?
Yes.
All of it? Or?
All of it.
Okay.
Yes.
Maybe I missed.
Or all that I wanted to say. Do you have any questions?
No.
Okay.
Not yet.
Okay. So the plan for today, and I'm hoping to finish all of this in the 1 hour that we have, is to talk about what is boosting. Basically set up the problem of boosting as something that came out of computational learning theory. And an answer to this question of boosting was this algorithm called Adaboost. And then I'll lead up to the more general ensemble methods. So let's talk about what is boosting. Boosting is a general learning strategy for constructing what is called a strong learner given a collection of rules of thumb, collection of weak learners. And it turns out that historically this was an answer to a question that was a question about that was phrased in the context of fact learning. And there was this paper by Rob Shapiro, 1989, called Strength of Weak Learnability, which answered this question. So let's set this up. Suppose you have a collection of rules of thumbs, a collection of weak classifiers, weak learners, not weak classifiers. A way of generating these kinds of rules of thumb, boosting is a way to create a classifier that is actually a strong one, and I'll define weak and strong more formally, using this ensemble. In general, an ensemble method is an ensemble is a kind of a learning algorithm or a way of generating classifiers that uses other classifiers as its building blocks. So you train a bunch of classifiers and somehow glue them up into one meta classifier that makes the final decision by consulting all these other elements of the ensemble. So think of it as a committee. And boosting is an ensemble method that has strong theoretical guarantees. So a lot of these slides are actually from a talk that Rob Shapir gave in the 90s, I think, and it's still kind of relevant. So, let's say you want to build a classifier that answers questions on the phone. So, you call up someone, you call up a phone service, and you ask, you want to be transferred to the correct location. And these examples are clearly dated, and some of you may not even understand what a collect call is. So let's pretend that there's something called a collect call. So let's say you pick up the phone and you say, I would like to place a collect call, and it has to be transferred to a desk called collect call, to a service called collect call. So it has to be labeled collect. This is even more funny. You have to talk to something called an operator, and you want to say that you want to make a call, but you need to bill it to my office. Then it has to be transferred to this service called third number. You'd like to place a call on your MasterCard, then it has to be transferred to this desk. I should update this. But you see the point. You say something, and based on what you say, it has to go to a different service. Now, what is interesting is that you can make easy rules of thumb. If the word card occurs, then predict, not predict, predict calling card. For example, if I was a programmer, I had to just hack up something, I could make these kinds of rules of thumb. It's easy to make up rules of thumb, but it's probably not so easy to get a good enough set of them that covers all possible cases. Is the example clear? So I can come up with hacky solutions that seem to work on these particular examples, but they may not be very good. The question is, can I combine these rules of thumb into a single prediction rule that does as well as all of them, but maybe hopefully better? And in some sense, we want to boost these rules of thumb into a single classifier. One way of doing this is you take and let's see how we might do it as people. I might see a small set of examples. All of them, for example, whenever the word card was said, I had to go to calling card. You derive some rough rule of thumb, like I just did. On these examples, this rule worked. So you have a rule of thumb. Now you throw them away. Now you take another set of examples, come up with another rule of thumb. If the word, what was the other one? If the word collect shows up, then the label should be collect. Again, maybe it worked on these 8 examples. You create a rule, I throw that set away. And I repeat this a bunch of times. I have a bunch of rules of thumb. And now, somehow, I need to combine all of them into a single rule. That's the game. Of course, this is not entirely clear. Yes?
So are these rules, are they classifying sequentially, like a decision tree, or all at once?
It could be anything.
Okay.
Internally, it's a black box. These rules, that's the nice thing about boosting and in general ensembles. They don't care about what is happening inside your the inner level classifier. You have a collection of classifiers. The goal is to somehow combine them. Internally, what is even more interesting is internally each of your weaker classifiers could themselves be other classifiers, produced by other learning algorithms. So you could have a decision tree. In fact, in your next homework, you'll be using decision trees, not decision trees, but decision stumps as your weak rules of thumb. That's also a heads up for those of you who had trouble with the decision tree homework. And I've told many of you in person that we'll be reusing your code. This is an opportunity for you to reuse your code. And if not, you might want to kind of revisit that a bit. So, it does not really care about what the internal classifiers are. We need to though specify how to select these subsets. Which, yes?
So when you say weak classifier is a classifier with low accuracy?
That's right. A weak learning algorithm is a learning algorithm that produces a classifier that is only slightly better than chance. Then slightly better than what we call the majority weighted. It's not great. It's not the kind of pack guarantee that you'll get a classifier that is whose error is less than epsilon. Instead, you get a classifier whose error is just slightly more than half. Sorry, accuracy is slightly more than half. That's a weak classifier. Now, in order to complete the story, I need to specify two things. One, I need to specify how do you select the subsets on which you train the weak classifier, or the rule of thumb, and I need to say how this combination works. Turns out boosting answers both these questions, or Adaboost, the algorithm, answers both these questions, and boosting is a way of asking a broader question about these things. So let's formalize this just to put some Greek on the intuition. I'm going to call a pack algorithm a strong pack algorithm if, in some sense, it's the stuff that we saw the stuff in the last week, we call them strong pack algorithms if for any distribution over the training set, for every epsilon and delta name, which means that for epsilon and delta that's as small as it can get, arbitrarily small, with only a polynomial number of examples, your strong pack algorithm will find a hypothesis whose error is less than epsilon, and it will find this hypothesis with probability 1 minus delta, which means for any epsilon, you should be able to find a classifier whose error is smaller than epsilon, right? So, which means that you should be able to get a classifier that's arbitrarily accurate with probability 1 minus delta. It's not always, but most of the time you'll get a classifier that's as accurate as possible. That's a strong pack algorithm. Yes?
Do you mean generalization error or training error?
Generalization, always generalization. The only thing we care about is generalization error. Keep that question in mind, because at the end I'm going to present something that is slightly bizarre involving generalization and training error. A weak pack algorithm is exactly the same, except that it can only do errors that are more than half minus gamma for some small gamma, which means the error will be close to half. The error in this case, in a strong pack algorithm, the error tends to 0. In this case, all we know is the error is less than half. Of course, it's between 0 and half, but we don't know, we can't say anything more than that. So the error, the weak learning algorithm produces a classifier whose error is just slightly better than chance. Yes?
Is this assuming that we're having Boolean labels?
Yes, binary classification.
Okay.
Yes, yes. But the idea generalizes, but all the theory that I'm going to describe and the algorithm that I'm going to describe is for binary. Yes.
Let's say you're doing something like using decision trees and building up a forest. Why wouldn't you want a lot of strong trees versus weaker stumps?
Oh, sure.
Is it a time complexity issue, or?
It's not a time complexity issue. If this works for the weaker ones, it definitely works for the stronger ones as well.
So just
That's one thing. Second thing, if you have bigger decision trees, each of them tends to overfit. This is always a trade-off. In real problems, we often don't have easy ways of generating really complex classifiers that are good enough. Yes?
I think like we used before, like in scikit-learn with the like random forest, I mean it only defaults, it caps the trees usually I think at like 10, depth of 10, and you only have like 10 of them, so like even there it's not going that far.
As the tree becomes bigger,
Yeah.
it tends to overfit, it tends to fit noise. So it gets worse.
Does boosting apply at all to regressions, or is it only classification?
Oh, it does. Ensembles apply to regression in general. Yes.
What's the definition of a stump?
A stump is a tree with whose depth is 1 or 2. I think 1. More broadly, you can think of depth-limited decision trees as your weak classifiers. Okay. Was there another hand? I saw half a hand. No? Okay. The question, this question was posed by a paper from Michael Kearns and Leslie Valiant in 1988. if I have a concept class for which I'm able to prove weak learnability, does this mean that concept class has a strong back algorithm? Does the question make sense? Suppose I have a concept class for which I have an algorithm that can produce classifiers whose error is slightly better than chance. Can I say something about, can I produce a strong back guarantee for this classifier? Does there exist an algorithm? I don't know what the algorithm is. I can't construct the algorithm, but does there exist an algorithm that can produce classifiers whose error is arbitrarily small? I don't know how to produce that classifier. I can only make these classifiers. I only have an algorithm that can produce a classifier that's better than chance. But maybe someone smarter than me can produce an algorithm that is as close to, that produces, that has an error as close to 0 as possible. Is that even true? Does weak learnability imply strong learnability? Does the question make sense? I want you to think about this question because it's not an obvious, there's no obvious answer. It's possible that there are concept classes for which weak learnability does not imply strong learnability. Meaning you can only produce these errors slightly better than chance, but that's the best you can do. There is no algorithm that can be arbitrarily accurate in the back sense. So this question was raised in this paper of Kearns and Valiant and it was not answered. Turns out, and so that set into motion a research agenda about this question of boosting. Can you boost weak classifiers into a strong classifier? And let's just go into some history. Yes?
So that means that there's no guarantee that for a weak algorithm always there is a better algorithm.
No, it turns out the opposite is. It turns out boosting is an answer to that question that says it is always possible if there was, in fact, that is the paper from Rob Shapiro, 1989. It's proved a way of converting a weak classifier, boosting weak classifiers into a strong classifier in a constructive way. If you give me a weak learning algorithm, or if you gave Rob a weak learning algorithm in 1989, he proved that he could convert it into a strong classifier in a methodical fashion without even knowing what your weak learning algorithm is. So this was called boosting. It was the first provable weak boosting algorithm that made 3 calls to your weak learner, produced 3 classifiers, and somehow combined them. And it was it did this more. There was a recursive thing. This Yoav Freund in 1990 wrote a paper that said that showed an optimal algorithm that boosts using majorities. There was some other work. In 92 there was a paper that tried to use these ideas in practical data, but at that time, computers were, 1992 is older than some of you, so computers were not very good, so there were some practical issues. In 95, so that was 7 years after the question was raised, Freund and Shapiro teamed up and wrote a paper on, introduced this algorithm called Adaboost that came with, that was not just a practically somewhat easy algorithm to implement, but also gave better guarantees over, it kind of answered this question in a concrete way. Adaboost is what we're going to look at, but Adaboost was followed by a lot of papers that used it in practical situations. It still sees application quite often, and it also managed to land the Godel Prize for Freund and Shapiro. So there's a lesson for grad students here. If you keep working on a problem, you might end up with the Godel Prize. Alright, so that's enough about history. Let's look at the algorithm itself. So is the setting clear before we go into the algorithm? Does the problem make sense? And is the idea, you should know what is what is a weak and a strong back algorithm. And the question that the Adaboost, or the question that Kearns and Valiant asked was, does weak learnability imply strong learnability? And through this research agenda on boosting, what showed up, what happened was, the answer was yes, weak learnability implies strong learnability. And here's the constructive proof of that in the form of an algorithm. And it's not just an algorithm, but also a theorem that says it works. Yes?
So when you say it's weak, does that mean you're slightly better than the majority label?
Slightly better than in the, yeah, let's assume I'm assuming that the classes are evenly distributed, so it's slightly better than half. In fact, for this situation, that's what we'll assume. But yeah, slightly better than the majority. Yes.
And strong learnable is back learnable?
Strong learnable is back learnable for arbitrarily small epsilons. So weak pack is exactly the same as strong pack, but the epsilon has to be is restricted. Epsilon is less than is only slightly better than slightly less than half. And how much? By gamma. All right. So before going into the algorithm, I want to present an intuitive version of this algorithm. So let's say that we have these 10 examples in our training set. Some of them labeled pluses and some of them labeled minuses. Our weak classifiers, our rules of thumb are either we get to put a line this way, this classifier, and say all of the examples on one side are positive and the other, or we get to put a line this way and say all the classifiers on one side are positive and the other side are negative. So we have axis parallel lines. Those are our rules of thumb. Initially, and this will become important later on. Initially, all these examples are equally important in deciding where to put the line. And let's say the best classifier on this data is this line. You put the line here and you decide that everything on one side is positive and the other side is negative. Let's call this classifier H1. So we've got a rule of thumb. Clearly there are mistakes. In this case, 3 out of these 10 examples are not correctly predicted. So the error is 0.3. Okay? So what you do next is actually the interesting way. You change the importance of the examples. You increase the importance of the examples that the classifier, your current classifier made a mistake on. So the size of these pluses, I don't know if the change is visible, but these pluses are bigger than these pluses. So this plus is bigger than this plus. So you increase the importance of the examples where you made a mistake, and you decrease the importance of the examples where that your current classifier got corrected. Yes?
In all of these claims, are we assuming that there's no noise in the test and training examples?
No, we don't know anything about noise. I mean, we are not making any such assumptions. This is a general situation. We are allowing for noise because we have that epsilon. We are allowing for epsilon in the epsilon error. So there might be noise, yes. And all of this is with respect to the training set. So you increase the importance. Yes, another question.
So, sorry, I was just confused with that, I guess, because it says, I don't know, it seems like to me, I guess it sounds like you're decreasing the import, or you're like making the examples that or I don't know, it sounds like you're making learners that were incorrect more important, I guess in that sense. I guess I'm more confused by
So
that part.
all the pluses and minuses here are examples.
Oh.
All the points
Oh,
here.
I think I see now.
And every point that your classifier was wrong on, you say, in the next round, these are the examples that matter. Every point that your classifier was right on, you say, these examples are less important. So you reduce the weight of those examples. You reduce the importance of those examples. And now you retrain. So let's remember the original classifier H1. Let's just use that space for remembering. And now you have a set of weights for each example. So dt is a set of weights that says how important is this example in round t. It's a number. So dt for this example is bigger than dt for this example at t equals 1. T is the round here, or t equals 2. This is the second round. So think of it as how much should the weak learning algorithm care about this example when picking its next hypothesis. So, for Adaboost, you need learning algorithms that know how to take into account the importance of these examples. We haven't seen such examples, such learning algorithms yet, but you should think about how you would modify, say, perceptron or or decision trees in a way that it takes these kinds of importance of examples into consideration while picking a classifier. But let's move on. So we have this D2 now, and now based on D2 you pick another classifier. This time you better, the demand that's made of the weak learning algorithm is it better get these 3 examples right, because those are more important. So it gets another hypothesis, and this also makes mistakes. How many mistakes does it make? So let me remove all the dashes that I placed. How many mistakes does it make? 3. So what did you say is the error of this classifier? There are 10 examples. Seems like it should be 0.3. But remember, we have this importance. The error is a weighted average of the importance. So even though you made 3 mistakes, those 3 mistakes, these 3 examples have a lower weight. Maybe 0.7. Each of them matters only 0.07, for example. Or each of them contributes lesser. So if all the examples contributed equally to the error, then they will the error is 0.3. But the 3 examples where you made a mistake were less important examples. So the error is a weighted average of the using the current set of weights. That make sense? So you have to, while computing error, you need to weight each example by its importance. Now, this can be written down formally in this form, and we'll tease it apart. This is the definition of error at the kth step. Let's think about what this means. So, if the true label is 1 and the prediction is -1, this product here is negative. In both cases, right? So, in both cases, yi times h of xi equals -1. So, what this means is for these examples, yi times, for the circled examples here, for these 3, yi times h of xi is -1. For all the others, for the ones that I'm putting, say, boxes on, where the classifier is correct, yi times h of xi is +1. So, let's apply this expression here. The error at time step 2, this is the second classifier, second time step, right? Is half minus times sum over. Let's pretend that all the examples are equally important for now, just to make this easier. If all examples are equally important, then d2 of t, d2 of I for all examples is 1/10. There are 10 examples, all of them are equally important. If that were the case, then this would be 1/10 times yi h of xi. So there are 7 examples where this is positive, there are 3 examples where this is negative, then this is actually not, let's compute it in the first round, just to make this clear. In the first round, this would have been half minus half times, there are 7 where this is positive, so 1/10 times 7 minus 1/10 times 3. There are 3 that are negative, where y times h is negative, which means you made a mistake. This is half minus times. Have I made a mistake here?
That's right.
If all examples were equally important, you get that the error is 0.3. So this makes sense. If all examples were not equally important, this just changes and examples that are more important get weighted. Okay? So this is the error at time step 1. On the other hand, you should go home and try out what happens when dt of I is not equal. Some i's have more importance than the others. What will happen is that the error will be dominated by whether the classifier got those examples right or not. Questions about this definition of an error before we go ahead?
So, does each classifier have its own weights for all of the examples?
Yes, that's
Okay.
d sub t.
Okay.
Where's that? The d sub t here. T is the round, right? Every weak classifier, every weak learner has its own importance, and that was the importance that was used to train it in the first place. That was the importance that was in play when the hypothesis was picked. Yes.
So in this particular equation is only valid, I guess, if for a binary classifier.
Yeah,
you need
yeah,
to
that's
adapt it for the.
You have to adapt it for multi-class and stuff like that.
Just to be clear, because I'm not completely clear on this. Each of the weak classifiers is classifying all of the data. You're not
Every weak classifier classifies every example.
You're not just working on the blue part of the graph.
No,
You said,
blue
okay.
means positive, red means negative here.
Okay. Okay.
Yeah. Yes, I should have said that earlier. Yeah. Okay, so the message here is we can calculate errors in a way that is informed by the importance of that example, of each example. And so we get a weighted average. So for and then the game continues. So we've got a weak classifier. Let's call this H2, this line here. And now this classifier makes an error on these three circled examples, and we repeat the process. We upweight examples where this round made a mistake on, and we downweight examples where this round was okay on. So you get a new set of importance. So you have increased the size of these circles, you've decreased the size of the examples where it was okay, all of these. All the pluses became smaller, all the circles became bigger. So you have a new weighted data set. So you don't just have data sets, but you have weighted data sets where examples are given importance. And you repeat the process. Now you have a weighted data set and you have the same. So you've got a entirely new set of DT, D3 this time. And now you train another weak classifier that tries to find a rule of thumb that makes as few errors as possible on the weighted example. And maybe this is the current rule of thumb. And around this time, again you compute the error and you continue. So you remember this weak learner, you get another box here, you calculate the error and you continue. Did you have a question?
Yeah, is this kind of like where we had perceptron and winnow where you can change the weights additively or multiplicatively?
There, remember, in perceptron and winnow, it's interesting that you make this analogy. Remember, in perceptron and winnow, you change the weights of features. Here you're changing the weights of examples. You have one weight for each example.
I guess my real question is, do we do it additively or multiplicatively?
Turns out you do it multiplicatively. Adaboost is actually a multiplicative update algorithm, but multiplicative updates not for features but for entire examples. We'll get to that in a minute. So at this point, again the same thing continues. You have the error. This classifier has an error of 0.14, even though you made how many mistakes? I think 3 mistakes here. You made 3 mistakes, but it's not 0.3, it's 0.14 because those 3 mistakes those 3 examples where you made a mistake are weighted very, very small. 0.14 is just a number I made up, but it's a small number. And you can continue, and you do the same thing again. You remember the hypothesis that you just trained, you update the DTs, and you can continue, but I got bored of making pictures, so let's say that we did it for 3 rounds. The final hypothesis that Adaboost produces is not any one of these, but a weighted combination of the predictions of each of these rules of thumb. So you have 3 rules of thumb, each of them makes a prediction, and each of them gets weighted by an alpha here, and the final hypothesis is the sign of this weighted thing. The final classifier is the sign of, so it should be the sign of these weighted rules of thumb. This is the intuition of Adaboost. Are there questions? Yes.
So the overall algorithm, or the overall classifier, weights the importance of the miniature classifiers, and the
Yes.
miniature classifiers weight the importance
Of
of the examples.
Yes,
Okay.
that's right. And so think of these alphas as a vote. Every weak classifier, H1, H2 and H3, each of them makes a prediction and it gets a vote. It's election season, so it's good to think of voting. Each of these classifiers, each of these weak classifiers gets a vote, but they're not equally important. Each of them gets a different weight in the final classifier. H1 gets a vote of alpha 1, H2 gets a vote of alpha 2, H3 gets a vote of alpha 3 in its decision. Yes?
Is DT used at all anymore, or is that just?
No, DT gets thrown out. So D1 was used to produce H1. It turns out D1 is also used to produce alpha 1. At that point, the D gets thrown out. So you don't have to remember, in fact, what part of the algorithm is how you have this one set of arrays for D, and you keep updating the D as you go along, because you don't need to remember it. DT plays an important role in the proof. It's a shame that I won't have time to go through the proof, but it's actually a fairly simple proof, and there's a pointer to the proof on the class website. But I'm jumping ahead because we haven't even come to the algorithm. Yes?
So is this like it's in dimensions, so hypothesis space?
Actually, that's a good way of thinking of it, because I call this H1, H2, and H3 weak classifiers, but in some sense you can think of them as feature extractors. So what you're doing is, by treating each of the weak classifiers as a feature, the prediction of the weak classifier as a feature, you're getting a linear combination of those features. So in some sense you're constructing features as you go along. Right? That's a good way of thinking about it. Yes?
How do you know how many of the weak?
Oh, that's a good question. That's a hyperparameter. So anytime I come to an uncomfortable question about how do you know how many, I make it a hyperparameter. It's a hyperparameter, you do it till you're happy. Yes?
So can there be a case when let's say I do it again, does the error increase? So do I just give it a lower alpha value?
That tends to happen. As you go along, alphas become smaller and smaller, and in fact at some point, if you're there are natural places to stop, and we'll get to that in a minute. Yes. Alright, so I feel like there's enough interesting questions that we should move ahead. Here's an outline of the boosting situation. You have a training set. Again, the same situation as always. You have instances that are x, I, and we have binding classifiers, so each of the yi's are plus ones and minus ones. Boosting proceeds in rounds. At each round, you construct a distribution on the examples. You have m examples, so you have a distribution dt on the m examples. You find a weak hypothesis such that that has a small weighted error on this distribution of the examples. Let's call the weighted error epsilon t. So you produce capital T such weak classifiers, and you construct a final output. Let's call it h final. So the important thing to know is really the only two things that I need to specify here are how do you specify the distribution and how do you construct the final output. Because the middle step, constructing the weak classifier, is outsourced to whatever rule of thumb that you use. If you use decision trees, this middle step would be to find a decision tree that has a low error on the weighted example. If you're using a 20-layer neural network, you leave it to the 20-layer neural network algorithm to find a low weighted error. You don't care. Boosting is a meta algorithm. It takes learning algorithms as a parameter and internally uses them again and again. The only thing that need to be specified in this meta algorithm are, one, how do you construct this distribution over the examples? And two, how do you construct the final output? And if I specify both of these things, I have given you Adaboost. I would have given you a boosting algorithm. Does that make sense? I am leaving this entire thing here unspecified because it can be whatever weak learning algorithm that you have, that you want to use. It doesn't matter. So let's look at the first one. How do you construct DT? And it turns out Adaboost answers both these questions. Adaboost gives a recipe for constructing distributions over examples, and Adaboost tells you, if you use this recipe for constructing distributions over examples, then here's how you should create the final hypothesis. So we have examples, m examples, and you need to specify a number over all these m examples such that the sum of these things adds up to 1. It's a distribution. We want a set of weights such that they all add up to 1. At every round, to remind you, the job of this is to specify how much should the weak learning algorithm emphasize errors on each training examples. If an example has a higher DT, then it should be emphasized more. If an example has low value of DT, then it's okay if the classifier makes a mistake on that. So in the beginning, at t equals 1, think of DT as just an array whose size is the number of examples. And the elements of the array add up to 1. In the beginning, at t equals 1, the recipe says, set all the examples to be equally important. In other words, you set dt, d1 of I equals 1 over m. There are m examples, so they are all equally important. Okay? The interesting thing is, after t rounds, what do we have after t rounds? You have dt, the current value of dt, and you have the hypothesis that was just produced using this dt, and you have the error of that hypothesis. So you have these three things. So you have the current distribution over examples, you just used your weak learning algorithm to produce a classifier using that distribution, that xt, and you have evaluated that weak classifier on the training set and produced the weighted error of that hypothesis. That's epsilon t. So you have these three things. What you want is, from the next round, is you want to, let's say this is done. In the next round, you want to find the next hypothesis that you want to find has to increase the importance of examples on which your current classifier made a mistake. It has to decrease the importance of examples on which your current classifier was okay. So it has to, in some sense, upweight examples where there was an error. It has to increase the value of dt where there was an error, and it has to decrease the value of dt where there was no error.
And all the time keeping the total 1.
Yes, all the time keeping the total 1. Yeah.
So I was just kind of wondering, in general, like, because I was trying to think of the kind of algorithms we've studied, and I'm not quite sure, like, how would you, in like, I guess any sort of the ones we've looked at, change the weighting of particular examples, I guess? How would you have that effect?
How do you have that effect?
How would you use that?
How do you use DT?
Yeah.
Let's think of perceptron, because I have a feeling that most of you kind of get perceptron because you've implemented it. Now, let's say you have an example that shows up, and I tell you, whatever happens, this example, make an update so that this example is, you don't make a mistake on this example. How would you change the update? What is the one thing that you have in changing the update? The learning rate. You can play with the learning rate so that on this particular, so the learning rate now becomes a function of dt. On examples that are more important, the learning rate is higher. On examples that are less important, maybe the learning rate is lower. That's for perceptron. For decision trees, you change the definition of entropy. Because when you're computing entropy, you're taking each example as being equally important. But now you have distribution over the example. So you can change the definition of you can kind of play with the entropy to account for the distribution of examples. And every algorithm you can do that in some way or another. Yes?
So I have a D1 and I move to D2. If I want to make a D3, will I look back into D2 or D1?
Just D2.
D2, yeah.
Yes. In fact, let's go to the update rule. The update rule is pretty simple. It seems rather complicated. Let's deconstruct it. You have a dt, like d1 for example, that's here. On an example that you made that you were okay on, you multiply it by e power minus alpha t. Right? And ignore the z for now. The z is just a normalizer that says all of them have to add up to 1. So ignore this for now. On an example that you were okay on, you multiply it by e power minus alpha t. What does that mean? If alpha, so let's think about what this means. What happens if alpha is greater than 0? You decrease. If alpha is less than 0, you increase. So I have taken all the heavy work into defining, I have abstracted it out into defining this alpha. On examples that you are okay on, you multiply by e power minus alpha t. On examples that you made a mistake, you multiply by e power alpha t. I haven't told you what alpha is, we'll get to that in a minute. If alphas were negative, for examples that you got the label correct, then this will do what we wanted. Right? If in fact, if in general, if alphas were positive, this will do what we wanted. If in general, if the alpha t is a positive number, do you agree this does what we wanted? So effectively, we need to find an alpha at time step t such that it's always a positive number. Then this takes care of what we want, of the fact that on correctly predicted examples, you get a promotion. A demotion. On incorrectly predicted examples, you get a promotion. I can summarize both of these into one step, like what we used to do all the time. The multiplicative update for each di at time step t, I as the example, is e power minus alpha times the product of y and h. The product of y and h will be positive if y and h have the same sign. It's negative if y and h have the opposite signs. So, yes.
Since t is also there in the exponent, that means that
Where's t in the exponent?
minus alpha. Oh,
It's
sorry.
alpha sub t.
Oh, sorry. Okay.
It's alpha, is the tth alpha.
Okay.
Yes. Did you? So, at this point, the only thing that's left to do is to specify what's this alpha. And what we desire is alpha should be a positive number. So let's now try to invent an alpha. Okay, let's see what the alpha is in fact. But before that, I want to remind you that this z is a fairly simple thing. All you have to do is just ignore the z, do this multiplication, and then add up all those things, and that gives you your z. And then divide by that z. That will make sure that the next d is also a probability distribution. All the numbers add up to 1. Z is a normalization constant. According to the prescription of Adaboost, is this quantity half of log of 1 minus epsilon divided by epsilon. Let's think about what's going on. I know that epsilon is less than a half. Right? The error is less than half because our classifier, our weak hypothesis, has an error that's less than half. That's the definition of a weak learner. If our epsilon is less than half, 1 minus epsilon is also less than half. Sorry, what did I say? 1 minus epsilon is more than half. Right? Which means 1 minus epsilon divided by epsilon is more than 1. Which means log of that quantity is more than 0. Which means half of that is also more than 0, which means that this alpha is at least same. I haven't proved to you that this is correct yet, but this alpha is at least same. It does what we expected. It promotes, if I plug in this alpha here, this will decrease the importance of examples where you made a mistake on. It will increase the importance of examples where you did not make a mistake on. It turns out this alpha does double duty. Remember that we needed a way of combining the hypotheses? This is the same alpha that we'll use for combining the hypothesis. This alpha is not just used in updating the D, it's also the vote that this particular hypothesis HT gets in the final prediction. Okay? So, we need a way of specifying two things. We need a way of specifying how to construct a distribution. I just showed you how. Now I need to say how to construct the final output, and the final output is after running this for t steps, what do we have? We have capital T weak classifiers, H1 through HT, and we have t values of alpha. Alpha 1, alpha 2, because we've just computed it. Each weak classifier takes an example and produces either a +1 or a -1, because it's a classifier. The final prediction, according to Adaboost, is the sign of sum of alpha times the prediction of each of the weak classifiers. It's the sign of the weighted average of the predictions. Okay? Questions? Yes.
So, in the examples you had before with the squares and how you switch from vertical to horizontal lines, so dt follows through those, the switch between those two?
dt is just, dt is used by the weak learning algorithm. dt has the following jobs. One, it's used by the weak learning algorithms to decide how much to weigh each example in deciding the classifier. And two, it's used for computing the error. And these are the only two things it does.
But it's shared between the weak classifiers.
No, dt no it's not, because after round t, dt is updated. And you start off with d1, you find a classifier, you find the epsilon, you find the alpha. Okay? And then you throw away d1, you go to d2. You use the d2 to find the h2 and alpha 2, h2, compute the error, epsilon 2, use the error to compute the alpha. Then you go to d3. So let's summarize this whole thing into one algorithm. You initialize d1 to be 1 over m, and then you go in rounds. First you find ht, whose weighted classification error. In fact, we don't even need to minimize the error. All we want is that the weighted classification error should be better than chance. You compute the vote for this ht. Alpha t is half log blah blah blah. You update the value of dt. dt plus 1 is dt times e power minus alpha y times h. You normalize it with z. And then you keep iterating this for t steps. You get capital T hypotheses and you get capital T alphas. And the final classifier that's produced by Adaboost is the sign of the weighted average. Yes?
So with this, I guess, algorithm also, would you need, if you somehow did end up with a classifier that was worse than chance, would you kind of just need to throw it away?
You're done. At that point, you stop learning because it's going to be a downhill thing.
Okay.
Yes?
Is the distribution IID here? Or
There's no, this distribution is constructed. There's no IID concept.
I'm asking because, like, how do you know what time you have to go by? How do you construct it?
How do you construct what?
The distribution.
The distribution is constructed exactly here. You initialize with all this. When I say distribution, think of this as just weights over the weightage given to each example. It's not, in some sense, it's actually changing the distribution over the training set, right? Initially, you assume that the distribution over the training set is whatever it exists because you have an equal weightage and there was an underlying distribution over labels.
But how do you pick a training set? Like how do
You don't get to pick. You never get to pick training sets. You only get to work with the training set that you have. I saw your hand and then your hand and then you. Yes.
You mentioned that the weak classifier can be treated as a black box.
Yeah.
So these weak classifier may be different kind. For example, the H1 is a perceptual and H2 is a decision.
It doesn't matter.
Doesn't matter.
It doesn't care, right? All you have to do is find a weak rule of thumb. Yeah. Someone here. Yes.
What's the alpha? This alpha, how do you choose the alpha? Do you have another version of this alpha?
No, this is the same alpha that's used here. This alpha t is defined to be half log 1 minus epsilon divided by epsilon.
It's based on some mass?
It's based on the error that was made on by the tth round. You had a question?
Yeah, two questions. Can we use something else instead of E, or is that part of the
No,
mathematics?
that is baked in.
Okay.
That is what gives you the theorem that I'm going to state next. Your second question?
Are we going to cover why this works?
I'm going to give you a theorem and I'm going to point you to the proof in the on the class website.
This might be a silly question. I've never seen it like that exp. How does it, is that just exp?
It's just e power, except if I write e power, think of, if I write e power minus alpha sub t, then you have the question of, is p multiplied? It's just,
so it just means e power whatever.
yeah. It's just a representational nightmare to put exponents and subscripts in them. Yes.
So I guess it seems like to me then, as you go along, EFT is generally going to be like lower for more specialized
Yeah.
classifiers. So I guess is that something that would be good? Because it seemed like then you would, the more general ones would get less of a vote.
No, but the alphas will appropriately change.
Okay.
Yeah. So let's look at the theorem because, someone asked a question about how long should you run. Capital T is a parameter to the learner. Alright, so in the toy example, just to remind you, each of your weak classifiers could have been lines that were axis parallel, but by taking these kind of an alpha weighted average of these weak classifiers, we end up actually with a hypothesis that was never in play. We might have started with just these axis parallel lines that were rules of thumb, but by taking a weighted average of these three things, we might end up with a classifier that we did not start, that was not in our original hypothesis space. In some sense, Adaboost explores a hypothesis space that is more complex than any of the weak classifiers. Alright, so let's look at the theorem. The theorem for Adaboost says the following. Let's say you run Adaboost for t rounds, and at each step let the error of the tth classifier be slightly better than chance. Namely, let's say it is half minus gamma t. And let's say all these gamma t's are more than some fixed gamma. So error is half minus gamma t at each step, and all these gammas are, so let's say that there's some gamma that's smaller than all the gamma t's. What the theorem says is the error of the final classifier that we construct has to be less than e power minus 2 gamma square capital T. In other words, if we have a weak learner, if we have a weak classifier, as the number of rounds increases, the error of the final classifier drops exponentially as you go along. The training error of the final classifier drops exponentially as you go along. And why does the training error matter? Because you remember the PAC theorem, the agnostic learning theorem that we saw? The test error will not be too far from the training error. So we are bounding, the final classifier has a very low training error. And the final classifier's training error drops exponentially as you run Adaboost more and more. The proof for this is actually fairly simple. Unfortunately, I don't have time to go over the proof. So I encourage you to actually look at the proof on the website. You seem to have a question.
I have a philosophical question.
Okay.
The people who come up with these groundbreaking algorithms, are they mathematicians or computer scientists?
I don't know the difference at this point. They are
because you might be able to implement an algorithm, but how do you come up with the...
We can talk about that offline. That's a philosophical question, yes. I often talk about the famous Richard Feynman algorithm for solving problems. You read the question, you think hard, and you write down the answer. Now, I want you to also think about what's the... It's not enough to just bound the training error because you can end up overfitting, but we have this pack guarantee that says if the training error is low, the test error will not be too bad subject to certain other conditions. It turns out in practice the training error for Adaboost, this is for some training set, for some data set, the training error after proceeding for a certain number of iterations invariably often ends up dropping to 0. You end up perfectly classifying the entire training set. What is even more interesting is that the individual epsilon t's as you go along, and this was raised by one of you, as you go along, the error of the weak classifiers as the rounds progress does not go down all the time. In fact, it even tends to increase. And yet the error of the final classifier decreases. The theorem tells us that it decreases exponentially, and this is in fact true. Here it decreases exponentially, often going to 0. What about the test error? The theory tells us that the training error will keep decreasing, and the theory tells us that the right thing to do is run Adaboost for infinite steps, because the error is proportional to something like this. So if you run Adaboost for infinite steps, the training error will keep going down. But of course, if you keep running Adaboost again forever, you will end up overfitting. So this capital T parameter is important, because if you run it for too long, the training error might keep going down, but the test error might end up going up. So you need to find a sweet spot. That's why you need to find a good T. There's some kind of unintuitive results that show up sometimes. In practice, the test error seems to flatten out, and this is a bit of a strange observation that led to a lot of head scratching by a lot of people. There have been many papers written on why this might be the case. There was an interesting paper by Shapir et al. In '97 which said that actually Adaboost also maximizes margins somehow, and it's not clear if that's the reason. But in practice, at least in some data sets, the test error does not go up as we expect because of overfitting, but it seems to flatten out. It's an empirical observation. There is some theory around it, but it's not entirely conclusive. Alright, so I am out of time and I'm not out of slides, so we'll continue in the next class.